Okay, for this problem, for the sample problem, determine the fixed and force vectors for the members of the two-span continuous beam as shown in the figure. Use the fixed and force equations given inside the front as given or illustrated a while ago. So this is our figure. So in our figure, this is a two-span, this is a two-members beam. So we have member 1 and member 2. The beam is loaded with a uniform loading, and it has an intensity of 2 kips per feet. And of course, for our beam, we have here our member 1, which has only a uniform loading, and member 2 is a combination of a uniform loading and a concentrated load, which is 18 kips. So now we're going to identify our member fixed end forces, or our Q's of F. So which means that for member 1, if we're going to have member 1, if we're going to isolate member 1, this is member 1. Of course, we have to assume that both ends are fixed. So it has a uniform loading. It has an intensity of 2 kips per feet. So therefore, if we're going to identify now our shear forces, you have the shear force at the beginning, and of course you have your moment force at the beginning, and of course you have your moment force at the end of the member, and you have your shear force at the end of the member. So for this one, this is a uniform loading. As mentioned a while ago, if that is a uniform loading, you have to go back to your TOS, or theory of structures. So which means that for this one, uh, you have the shear force. The formula for the shear force for uniform loading is WL all over 2. So this is the shear force, WL all over 2. So which means that all throughout of the member 1, this is a uniform loading. So which means that the shear force at the beginning of the member is equal to the shear force at the end of the member. So our W is 2, our L of the length of the beam is 30 all over 2. So you simply have 30 kips. So which means that the shear force at the beginning of the member and the shear force at the end of the member is also 30 kips. Now for the moment force, our F sub m, moment force is equivalent to 2W squared all over 12. So this is the formula for our moment force. So which means that the moment force at the beginning of the member is positive 2 times 30 squared all over 12. So that is equivalent to 150 kips feet. Then at the end of the member, it will have a negative 2W squared all over 12. So we simply have now negative 150 kips feet. So this is now the value for our shear fixed end forces in the local coordinate system, of course, for member 1. So if we're going to write that in matrix form, so you have now your Q's of F. So this is our member fixed end forces, or Q's of F1. So this is the member fixed end forces for member 1, and this is the Q's of F sub 1 to denote that 1 refers to member 1. So if you have to write that in matrix form, you have your F sub S at the beginning is 30, F sub M at the beginning is positive 150, F sub S at the end of the member is 30, and F sub M at the end of the member is equivalent to negative 150. So we have now identified our Q's of F1, or the member fixed end forces at the end of the member for member 1. Now we move on to member 2. So if we're going to observe member 2 class, so this is our member 2. So member 2 here is a uniform loading, a combination of uniform loading and concentrated loads. Of course, uniform loading is 2 kips per feet, and our concentrated load is 18 kips. So if we're going to identify our member fixed end forces for member 2, there will be two formulas. The shear forces and the moment forces. The formula to that will be the formula for the concentrated load that we have presented a while ago, and the formula for uniform loading that we have used to solve for the shear forces and the moment forces for member 1. So for this one, These are now the values for our shear forces and moment forces at the beginning of the member and at the end of the member. So the first one, of course, this is the formula for our concentrated load. This one is the formula for our uniform loading. So we have to add. So the shear force for the concentrated load plus the shear force for the uniform loading at the beginning of the member. Simply have to substitute the given values for our variable, and we have now the value which is 43.33 kips. Then we have the moment force at the beginning of the member, so which means that this is now the concentrated load, the moment force for the concentrated load, then plus the moment force for the uniform loading, and that is equivalent to 230 kips feet. So which means that for this one, we are going to have now the shear force at the end of the member and the moment force at the end of the member. You simply have to substitute again the variables, the value for the variables to our equations. So we have 34.66 kips and negative 190 kips feet. So you have to take note if this is member 2. So you have member 2, so which means that this one is our concentrate uniform loading, and of course we have to assume that both ends for a member is fixed, and you have your concentrated load. So that is the position for our member 2. Those are the loadings, and you have to identify, of course, the capital letter L, and you have to identify capital letter L as the length of the member. Our small letter small letter L, you have L sub 1 and L sub 2, which is now the refers to the location from the end point of our member towards our concentrated load. So as illustrated or identified in our figure. So now we have the value for our shear forces and moment forces. So which means if you're going to write that in matrix form, this is now the value for our fixed end forces in the for member 2. There are fixed end forces for member 2. So you have here, this is our F sub S at the beginning of the member. This is F sub M at the beginning of the member, F sub S at the end of the member, F sub M at the end of the member. So respectively, so you have 43.33, 230, 34.66, and negative 190. So in matrix form, you have written the value for our member fixed end forces for member 2. Now we move on to structure stiffness relation. So for beam, the structure stiffness relation is actually equivalent to P minus P is equal to SD plus P sub F. So of course, in our previous discussion in plane truss, we were introduced that our for the structure stiffness, P is equal to S times D. Here we have for the beam, this will be our structure stiffness relation. So P is equal to S times D plus P sub F. Still, our P is the joint load vectors. Our S is the structure stiffness matrix. Our D is the degrees of freedom or the displacement that we will be solving, of course. Our P sub F is the structure fixed joint forces, P sub F. So this can also be written as P minus P sub F is equal to S times D. So how are we going to identify? Still, of course, the value for our joint load vectors, we could easily identify our P through inspection based on the original beam using the external forces that is acting on the joints. For our S, we have to assemble our S. How do we assemble? Still, we're going to make use of assembly of the structure stiffness matrix by member code numbers. So which means that the procedure that we have identified or we have solved for plane truss, the same procedure we have. So we're going to identify for the structure stiffness relation, we have to identify our K. So for the beam, since we don't have transformation matrix, meaning to say we don't have our global coordinate member and forces in the global coordinate system, since the members of the beam are directed in one direction. Unlike for plane truss, the members of the beam are not directed in one direction, because if you're going to observe, there are beams that is in horizontal, there are members that is in horizontal, vertical, or inclined for the plane shafts. So they are not directed in one direction. However, for beam, the members of the beam are directed in one direction. So which means we have only here one direction for our members. So for example, in our illustration, we have in horizontal direction. So that is the direction for our members for the beam. So which means that we don't have here our value for consideration for our member and forces, which is denoted by capital letter F. We only have our Q. So we did not transform that one into global coordinate system, our member and forces. So now, for us to assemble our structure stiffness matrix, we're going to make use our K, which is our structure stiffness in the local coordinate system, which is small letter K for the beam. So same procedure, you have to identify your K for each member. So since, for example, we have 3 members, so you're going to have K sub 1, K sub 2, K sub 3. So member 1, member 2, and member 3. Then same procedure again, you have to identify our code numbers, which means that in our previous discussion, we identify the code numbers, which is the number of the restraint coordinates and degrees of freedom at the beginning of the member and at the end of the member. So what we have done before, same procedure. So still, the first and second column refers to the beginning of the member. The third and fourth column refers to the end of the member. The first column at the beginning is your along x direction. The second column is along y direction. Then at the end of the member, the first column is along x direction, and the fourth column will be along y direction. So that is, then you have to identify the number for whether at the beginning of the member or at the end of the member there is a presence of restraint coordinates and degrees of freedom. Identify those numbers, then you have to write. So same procedure what we have done on plane shafts. So we have here 4. For example, for this one, you have 4, 5, 1, and 2. Whatever is written on top should be written on the side. Then similarly for member 2 and member 3. So once you have identified those K and the member code numbers, you can assemble your S, which is our structure stiffness matrix. So assemble our S, same again, same procedure, identify the number of degrees of freedom. So for this illustration, there are 3 degrees of freedom. So we have here on top 1, 2, and 3 to represent the column. Then whatever is written on the side should be written on the whatever is written on the top should be written on the side. So we have here 1, 2, and 3. This represents now for the rows in our S for the structure stiffness matrix. So similarly also for our small letter K, whatever is written on top should be written on the side. Then afterwards, as we discussed before, for our S now, to have this value for our S, those elements, so we simply have to identify the code number 1 and 1. For member 1, if there is, then you write the value. For member 2, if there is, you have to add. Then member 3, you have also to add. Then and so on and so forth. So 2 and 1, so same procedure. So then you try to simplify. So once you simplify, you can have now the value for your S or the structure stiffness matrix. So this can be written, for example, as you simplify, you have the value which is -4, 3. You have here 1, 2, 5, 4, and 5. So this is now the value for your structure stiffness matrix, your S. Now, how do we identify the value for P sub F? P sub F is our structure fixed force vector. So to identify the value, we have to solve first for our Q sub F. So to solve for Q sub F or member fixed and forces, we use the formula that we have used in solving for member fixed and forces for a certain for every beam. So you're going to make use of that. Then once you have now your Q sub F for your member 1, member 2, member 3, for example, you have 3 members, identify the code numbers. So the code numbers, so same procedure, you have to identify the code numbers at the beginning of the member and at the end of the member. For example, for this one, you have at the beginning and the end of the member, so you have to write that on the side. Since once you have that one, you could identify now your P sub F. Then the P sub F is actually in the location and position of your degrees of freedom. So it is equal to the number of degrees of freedom. So you have to write that one. And you have now to identify